At the heart of a distant galaxy lies a black hole so massive it could swallow 33 billion suns. Its gravity bends light itself, yet for years it remained invisible. Tonight we'll uncover the secrets of Abell 1201 BCG, one of the universe's most colossal enigmas. If this fascinates you, please like, subscribe and share, and tell us in the comments, what do you think hides beyond its event horizon? Thank you for watching. Now, let's begin. At the largest scales, the universe presents a web of matter that spans hundreds of millions of light years, and within this structure the galaxy cluster called Abell 1-2. 0-1 sits at one of the junctions where filaments meet. The cosmic web forms as gravity amplifies small early ripples, so that denser regions attract more matter, while emptier regions become wide voids. A galaxy cluster is the most massive bound outcome of this growth, containing hundreds to thousands of galaxies, a dominant reservoir of dark matter, and a vast volume of thin hot gas known as the intracluster medium. Abell 1-2, 0-1 lies at a moderate cosmological distance, so the light now reaching Earth began its journey roughly 2.7 billion years ago, and shows the system as it was at that earlier time. Distance on these scales is described by redshift, the stretching of wavelengths by the expansion of space. A modest redshift places this cluster in a mature universe where structure continues to evolve, but the broad cosmic pattern is already set. On the sky, the cluster appears not as an isolated island, but as a swelling in the mass field, an overdensity that gathers galaxies along connected filaments and influences motions over very large volumes. Those filaments channel groups and individual galaxies inward for very long times, and they also carry gas that helps define the environment into which arriving systems fall. The inner region, where orbits are bound, grades outward into a zone of continuing infill, so the outskirts record the slow arrival of fresh material guided by the web. These features rest on the background cosmology, in which space expands, and the light from distant sources shifts toward longer wavelengths as it travels. The amount of shift preserves information about the scale factor and the history of expansion, driven by matter radiation and dark energy, and that information ties the observed spectrum of the cluster to a consistent distance. At large radii, several signatures announce the presence of a cluster. Galaxies become more numerous on the sky, the hot gas shines at X-ray wavelengths, with temperatures of tens of millions of degrees, and the total mass slightly distorts the shapes of still more distant galaxies by gravitational lensing. These signs appear together in wide field observations and confirm that Abell 1-2, 0-1 is a regional mass concentration extending over many hundreds of thousands of light years. The surrounding intracluster light adds a faint background made by stars that no longer belong to any single galaxy after tidal encounters. This glow becomes stronger toward the center in many systems and signals a long record of mergers and accretion. Even at this outermost viewpoint, one can describe the setting without turning to inner details. The filaments that connect to the cluster may be faint to direct imaging, yet they are gravitationally important because they feed mass into the system and align orbits so that preferred directions persist for billions of years. Within this network, the brightest cluster galaxy anchors the visible center of the mass peak, but it does so as part of a hierarchy that extends far beyond any single galaxy. Light from the cluster crosses multiple voids and lesser structures on its way to Earth, carrying information about composition, motion and temperature that observers read with imaging and spectroscopy to build a coherent view of the region. Distances follow from measured redshifts and a well-tested expansion history. Galaxy distributions come from deep optical and infrared images, gas temperatures and densities come from X-ray spectra and surface brightness. Together, these measurements place the cluster within the broader map of the cosmic web and establish the scale, mass, and dynamical state at large radii. In Abell 1201, the large-scale gravitational field dominates the motions of member galaxies, so orbits trace the pull of the whole, while the outskirts show evidence for ongoing accretion along the main filaments. The field extends far outward and changes only slowly with time at the epoch seen, because the system has already assembled much of its mass even as the web continues to supply new material. The line of sight from Earth to this cluster therefore samples a representative portion of the universe at moderate distance, and the object appears as one node among many rather than a lone outlier. Classic catalogues and modern surveys agree on this broad identity, a deep potential well filled with galaxies and hot gas, and embedded in a more extended dark matter halo. The contrast with the lower density field helps to set expectations. In the field, encounters are rarer, and tides are weaker, while in clusters, frequent passages and crowded orbits foster transformations that add to the intracluster light and alter galaxy structures over long timescales. Abell 1201 participates in this general ecology of growth and interaction. Because the scales are so large, any description at this level depends on careful use of light. Light that left the cluster when conditions on Earth were different now arrives slightly redder. Precise spectra measure that shift, and with standard cosmological parameters they return a distance near a few billion light-years. Images of the surrounding sky reveal alignments and number counts that allow modeling of the projected mass distribution, while the weak shear in background galaxy shapes provides a statistical reconstruction of the unseen matter that does not rely on luminosity. These reconstructions show an extended, roughly elliptical pattern that becomes denser toward the center, and includes substructures associated with infalling groups consistent with continuous growth guided by filaments. In maps of the hot gas, the large-scale gradients appear smooth as expected when gas has settled into quasi-hydrostatic balance within a deep potential. The total X-ray brightness depends on density and temperature, integrated along the line of sight, so it offers a check on mass estimates that come from the galaxy motions and the weak lensing signal. Taken together, these outer-scale observations outline a gravitational landscape with a broad valley whose floor hosts the luminous heart of the system. The cluster's position in the web influences how material approaches from different directions, and the outer mass distribution often aligns with the most prominent filament. Such alignments are common outcomes of anisotropic accretion and help explain the overall shape seen in wide-field images. As an observational object, Abell 1201 is therefore first understood as a node in the network with a high galaxy number density compared to the field, diffuse hot gas at very high temperatures and weak lensing signatures over hundreds of thousands to millions of light-years. This perspective fixes the absolute context by giving the system a cosmic address, a look-back time set by light travel, and a characteristic physical scale far larger than any single galaxy. From this vantage, one can speak clearly about what surrounds the central luminous body without invoking inner specifics, an extended dark matter halo enclosing a population of galaxies and permeated by hot gas all embedded in filaments and voids. This outer view serves as the starting point because it supplies the measures of mass scale and environment that any more detailed account must respect, and it relies on observations that reach across the full breadth of the cluster rather than on local features. Observers sometimes describe a notional boundary called the virial radius, meaning the scale within which the system is close to dynamical balance. Beyond this distance, the flow of new material dominates. wide surveys at optical, infrared, radio, and X-ray wavelengths sample these domains with complementary strengths, so the census of galaxies, the mapping of gas, and the measurement of weak shear can be compared on common angular scales to build a consistent mass map. In this way, the large-scale portrait of Abell 1201 becomes a measured picture rather than a schematic grounded in light gathered across the spectrum and analysed with models that respect both gravity and the expansion of space. The infill regions around a galaxy cluster form a broad transitional zone where matter that once drifted with the general expansion of space now turns around and begins a long descent toward the deep gravitational well, and in Abell 1201 this zone connects to the cluster along several filaments that act as highways for galaxies' gas and dark matter. A filament in this context is a bridge of enhanced density that stretches for tens to hundreds of millions of light years, made mostly of dark matter, with a lesser share of gas and stars, and it arises as gravity draws material into elongated features that intersect at nodes where clusters grow. The term turnaround radius marks the scale at which the local gravitational pull balances the expansion for a given shell of matter, so beyond that distance material continues to recede with the Hubble flow, while inside it the matter slows, stops and falls inward. Just inside the turnaround boundary lies a region called the splashback shell, defined by the outermost apocenters of freshly accreted orbits. In maps that stack many clusters, this boundary appears as a steep drop in galaxy number density and provides a physical marker for the edge of the system. In single clusters, the signature can be blurred by aspherical accretion and the time since the last major infall event. Yet the concept remains useful, because it tells where material has completed at least one orbit, and where it is on its first inward plunge. Along the filaments feeding Abell 1201, small groups and pairs of galaxies travel together, and their internal tides loosen stars from faint outer envelopes, long before the groups reach the main potential, a process often called pre-processing. Dwarf galaxies in these streams can be stripped of gas by the combined effects of tidal forces and the rising pressure of the ambient medium, and some lose the ability to form new stars even before they cross into the brighter core. The gas that rides in with these groups does not remain cool. As it encounters the outer reaches of the cluster's gravitational field, it accelerates and can meet previously accreted material along a broad, roughly spherical shock, converting bulk motion into heat and helping to build the hot, thin plasma that fills the space between galaxies. Observers describe this broad outer transition by combining several kinds of measurements. Weak gravitational lensing slightly distorts the shapes of still more distant galaxies behind the cluster, and reveals projected mass along and between the filaments, while counts of galaxies with similar redshifts trace where the number density rises above the background along preferred directions. Radio surveys map long, faint ridges that sometimes coincide with shocks, where electrons receive fresh energy, and X-ray images show where gas density and temperature rise as the flows converge. Together, these maps emphasize that the outskirts are not smooth spheres, but anisotropic structures that reflect the directions of the main filaments and the assembly history of the node. Kinematics in the infall region retain memory of this pattern. The velocity field of galaxies entering along a filament shows a dominant inward component with substantial scatter from orbital pitch angles and group internal motions, while a smaller population of backsplash galaxies moves outward on first return, after pericenter reaching apocenters near the splashback shell before turning in again. Because the cluster is not viewed in complete 3 dimensions, inferring the true orbital distribution requires models that translate line-of-sight velocities and projected positions into likely orbits. but even simple diagnostics reveal coherence along major filaments, where the mean infall speed is higher and the dispersion broader. The lights of the galaxies also change gradually with environment. Compared with the field, the infall population shows a rising fraction of quenched systems that have ceased forming new stars, a trend strengthened by preprocessing in groups and by early interactions with the gas that envelopes the cluster. Tidal debris accumulates in long, faint streams that over many orbits add to the diffuse intracluster light. This glow is most obvious near the center, but it traces a history that begins far out, where slow encounters unbind the most fragile stellar halos, and where satellite galaxies lose mass on their first approach. The dark matter skeleton that underlies these processes does not radiate, yet its shape governs how and where accretion proceeds. Numerical models that match the statistical properties of large surveys predict triaxial halos aligned with their filaments, and observations support this tendency through alignments of the galaxy distribution weak lensing shear patterns and the elongation of the hot gas at large radii. In the case of Abell 1201, the large-scale elongation on the sky and the preferred directions of associated groups suggest one or more dominant filaments that continue beyond the mapped field, consistent with the general picture of a cluster growing at a node. Timescales in these outskirts are very long. A galaxy starting just inside the turnaround boundary can require several billion years to complete a first orbit, and during that time it experiences changing external conditions as density and pressure rise toward the center. Ram pressure, the drag exerted by motion through thin gas, increases with both density and speed, and it can displace or remove a galaxy's own gas even without a head-on collision. Tides act more gradually but cumulatively, altering orbits and morphologies, and together these processes change the mix of types seen as one moves from the field through the infall region into the denser cluster interior. Yet the outer domain remains a place of first contact rather than completed transformation, and many systems there still resemble their field counterparts except for faint signs of disturbance. The global mass profile also reflects the growth at the edge. In a self-similar description, the density falls with distance in a smooth way, but the actual profile can show small bumps where recent infill has added mass along a particular direction. These features relax away over time as orbits phase mix, yet the detection of infalling clumps in number density maps and lensing reconstructions shows that the approach of fresh material is ongoing. The thermal history of gas follows a similar arc. Cool streams may survive partway inward along filaments shielded by their own inertia before being shock-heated and mixed into the ambient medium. Where shocks form, temperature and entropy rise, and the gradient of these quantities across the outskirts holds a record of how rapidly and from which directions the cluster has grown in the recent past. Because the outer layers are so extended, observations must trade detail for coverage, and many inferences rest on stacking many clusters with similar properties to recover weak average signals. Even so, case studies that combine deep imaging, spectroscopy lensing, and high-energy data can reveal the skeleton of filaments and the imprint of recent accretion in single systems. In Abell 1201, the convergence of galaxies along particular position angles the smooth but not perfectly round envelope of hot gas, and the mass pattern, reconstructed from weak shear together, support a view in which the infall region remains active and anisotropic. From this vantage, the cluster is not a static island, but a crossroads where long threads of matter deliver new arrivals that will over long times feed the central potential. The outskirts, therefore, set both the boundary conditions and the initial states for everything that later unfolds deeper in, and by measuring them carefully, one fixes the flow of mass and energy that shapes the evolution of the system on its largest accessible scales. The space between galaxies in a cluster is not empty, but filled with a very thin, very hot plasma called the intracluster medium. And in Abell 1201, this medium makes a luminous atmosphere whose pressure and temperature record the depth and shape of the cluster gravitational well. The gas reaches temperatures of many tens of millions of degrees hot enough that its atoms are stripped of most electrons, and it shines in high-energy X-rays through a process called thermal Bremsstrahlung, which means free electrons scattering off ions and losing energy as light. Because the gas is so rarefied, a single cubic centimetre would contain far fewer particles than even the best laboratory vacuum, yet the intracluster volume is so vast that the total mass of this plasma rivals or exceeds the mass in all the stars of the member galaxies combined. The structure of this atmosphere reflects a slow settling within the cluster potential. In a state called hydrostatic equilibrium, the outward pressure gradient of the gas balances the inward pull of gravity at each radius, so that pressure falls smoothly from the center to the outskirts, while density and temperature also decline with distance. Deviations from this balance carry information about recent infall mergers or stirring by galaxies and subhalos moving through the medium. Maps of surface brightness and spectra measure the temperature and density as functions of position on the sky, and yield pressure and entropy profiles that show how the gas has been heated and arranged over long times. Entropy in this context refers to a quantity that increases when gas is shock-heated and decreases when it cools, and its rise with radius marks the imprint of accretion shocks at the edges of the cluster, where fresh material is converted from bulk flow into hot plasma. Another handle on the intracluster medium comes from the Sunyaev-Zeldovich effect, which is a small change in the spectrum of the cosmic microwave background, where background photons gain energy from passing through hot electrons. This effect depends mainly on the integrated pressure along the line of sight and complements X-ray measurements that depend more strongly on density. By combining the two, observers infer three-dimensional distributions of temperature and pressure that are less sensitive to small clumps than either method alone. In Abell 1201 wide-field imaging in X-rays would show a smoothly declining glow that is not perfectly round but slightly elongated along the same directions traced by galaxies, and weak lensing shear a pattern that hints at the underlying triaxial shape of the dark matter halo and the guidance of filaments seen in the outskirts. Within this glow, subtle features often appear. Gentle ripples can mark weak shocks or sound waves, while faint edges can signal cold fronts where gas with different entropy has slid past neighboring layers without mixing. Such structures arise as subclusters fall in, as galaxies stir wakes, or as bulk motions and turbulence carry energy across tens to hundreds of thousands of light-years. Turbulence and bulk flows add non-thermal pressure support, which means that part of the resistance to gravity is carried by motions rather than by thermal pressure alone. Accounting for this support matters when using hydrostatic equilibrium to estimate mass from X-ray data, because neglecting it can bias the mass low by a modest but non-zero fraction in regions where flows remain strong. Clumping of gas at low densities in the outskirts adds another source of bias, because emission scales with a square of density so small, overdense knots can brighten the average signal. Careful analysis uses azimuthal medians, high-resolution imaging and cross-checks, with the Sunyaev-Zeldovich effect to reduce these biases. The composition of the intracluster medium also carries a record of the cluster's history. Although hydrogen and helium dominate, there is a trace population of heavier elements made in stars and spread into the intracluster space by galactic winds and by stripping during past encounters. X-ray spectra reveal these elements through emission lines and show that the plasma is enriched to a level that varies with radius typically higher toward the center, where the brightest cluster galaxy and its predecessors have had the longest time to pollute the surrounding gas. The pattern of enrichment, including the ratios of elements associated with different kinds of supernovae, tells how many generations of stars contributed and how the products were transported outward. Transport itself is a subtle subject in this environment. Thermal conduction could in principle move heat down temperature gradients over long distances, but magnetic fields thread the plasma and can reduce the effective conductivity by aligning electron motions along field lines. Viscosity, which tends to damp small-scale motions, is likewise shaped by magnetic geometry and microphysics. These processes determine how quickly shocks broaden, how sharply cold fronts persist, and how rapidly turbulent eddies decay. In many clusters, long-lived edges and narrow features indicate that conduction and viscosity are suppressed, compared with simple expectations for an unmagnetized plasma, allowing multiphase structure to endure for long periods. Cooling is a central question for any hot atmosphere. In the densest regions of a cluster, the gas can in principle radiate away its thermal energy in less time than the age of the universe, a path that would lead to a steady inward flow of cooling gas. Observations in many systems, however, show that actual cooling to low temperatures is much reduced compared with the naive expectation implying that heating of some kind offsets most of the losses. On the large cluster scale, this balance expresses itself as a central plateau in entropy rather than a runaway drop. At the radii considered here still far from the very center, the cooling time remains longer than a Hubble time, and the gas behaves mainly as a slowly evolving tracer of the gravitational potential, rather than as a rapidly changing multiphase medium. Pressure profiles built from X-ray and Sunyaev-Zeldovich data in many clusters display a near-universal shape when scaled by characteristic radii and densities, and Abell 1201 would be expected to follow this trend with modest departures, where recent accretion or asphericity is strongest. The smoothness of these profiles supports the idea that most of the gas is in approximate hydrostatic balance, while small departures encode the imprint of ongoing growth. The interplay between gas and dark matter is visible in another way. Because the gas can radiate and shock while dark matter cannot, the gas distribution is rounder and less clumpy than the total mass at the same radii. Comparisons between X-ray, isophotes, Sunyaev-Zeldovich maps, and weak lensing reconstructions therefore reveal differences that highlight how baryons and dark matter respond differently to the same potential. These comparisons, applied carefully with attention to projection effects, provide a cross-check on mass models and increase confidence in the inferred depth of the cluster potential well. As a dynamic medium, the intracluster plasma is also a laboratory for collisionless processes. Particle distributions can depart slightly from perfect thermal shapes, and weak shocks and shear layers can accelerate a small fraction of electrons to relativistic energies, producing faint radio emission in halos and relics that outline places where energy is being transferred from bulk motion to particles. The present shape and brightness of such radio structures offer additional clues about the past and present stirring of the gas and its magnetic field strength and geometry. In the outer regions, the plasma is still settling from recent accretion, so turbulence can be stronger and thermodynamic profiles more slowly rising. In the inner regions of the cluster scale, short of the galaxy, and well outside the domain dominated by a single central object, the profiles become smoother and the gas more nearly stratified. But even there, gentle sloshing motions can persist for very long times after minor perturbations. Through all these features, the intracluster medium serves as a readable record of how mass accumulates, how energy is dissipated, and how gravity sculpts matter on the largest bound scales. It is both a messenger that carries information about the cluster potential and a participant that responds to tides, shocks, and flows. And by measuring its light and its imprint on the background radiation, one reconstructs a three-dimensional atmosphere that connects the broad infall region to the denser interior without presuming the details of smaller inner structures. Dark matter defines the backbone of a galaxy cluster, and in Abell 1-2, 0-1, the invisible component outweighs stars and gas by a wide margin, shaping orbits, temperatures, and the bending of light across scales of hundreds of thousands to millions of light years. Dark matter in this setting interacts mainly through gravity and leaves its imprint through three complementary observables: the velocities of galaxies that move within the potential, the pressure-supported shape of the hot intracluster medium, and the weak distortion of still more distant galaxies by gravitational lensing. Together, these measurements describe a triaxial halo whose density rises smoothly toward the center and falls with radius in a form that universal halo models capture with a small set of parameters. A common description uses a profile that is steeper than a constant density core and shallower than a pure power law, with a characteristic scale where the logarithmic slope changes. The precise parameters vary from cluster to cluster and depend on assembly history, but the overall pattern holds in a wide range of observations and simulations. Because dark matter does not radiate, it does not dissipate energy the way gas does, so the halo retains elongated shapes and substructure that reflect how matter accretes along filaments. In projections on the sky, the mass distribution therefore appears slightly elliptical, with its major axis often aligned with the main infall directions seen at larger radii, and Abell 1-2-0-1 fits this general behavior when reconstructed from weak gravitational shear. Weak lensing measures small coherent alignments in the shapes of many background galaxies, an effect averaged over large samples to overcome noise. The resulting shear map translates through an inversion that accounts for projection and for the mass sheet degeneracy into a smoothed picture of projected mass. In this picture, the halo of Abell 1-2, 0-1 shows a broad peak centered near the brightest cluster galaxy, and gentle declines toward the outskirts with hints of small plateaus or ridges, where recently accreted groups contribute additional mass. Independent of lensing, a census of galaxy velocities builds a dynamical model. Member galaxies move in 3 dimensions under gravity, and their line-of-sight speeds measured from redshifts form a distribution whose width reflects the depth of the potential well, while its radial variation reflects the balance between radial and tangential orbits. Converting this information into a mass profile requires an assumption about the anisotropy of orbits, because radial motions and tangential motions produce different dispersions at the same mass, but a family of models can be tested, and the ones that match both the velocity dispersion profile and the number density profile tend to agree with lensing mass within reasonable uncertainties. A complementary approach uses the caustic method in phase space diagrams of line-of-sight velocity versus projected radius. Trumpet-shaped boundaries emerge where the escape velocity declines with radius, and their amplitude traces the cumulative mass without assuming equilibrium. These dynamical reconstructions applied to Abell 1-2. 0-1 yield a halo mass that explains the observed high temperatures of the intracluster medium and the amplitude of the weak lensing shear knitting the 3 lines of evidence into a self-consistent picture. The hot gas itself adds an additional cross-check. If the atmosphere sits close to hydrostatic balance, then the measured pressure gradient translates into the gravitational acceleration, and hence into enclosed mass as a function of radius. Non-thermal pressure from bulk flows and turbulence adds to the support, and if unaccounted for, it can cause purely hydrostatic masses to come in slightly low relative to lensing masses. By comparing X-ray and Sunyaev-Zeldovich derived pressure profiles with lensing reconstructions, one can estimate the fraction of non-thermal support and refine the total mass profile. In many relaxed clusters, this correction is modest in the intermediate radii, and the shapes of the profiles match well within uncertainties. Asphericity complicates all these inferences because an elongated halo viewed along its major axis appears more concentrated than the same halo viewed side-on. Abell 1, 2, 0, 1. Like most clusters, likely departs from perfect spherical symmetry, so analyses that include triaxial geometry and allow for misalignment between mass and light give a more faithful estimate of concentration and scale radius. Subhalos, which are bound clumps of dark matter associated with individual galaxies, or in falling groups, further perturb the lensing signal and the velocity field. In projected mass maps, they appear as small enhancements that can be traced to luminous counterparts, and their cumulative abundance and radial distribution provide a record of tidal stripping and dynamical friction within the larger halo. These processes act over long times, removing mass from the outskirts of subhalos and depositing it into diffuse components that add smoothly to the main potential. The full halo therefore contains a mix of a dominant smooth component and a spectrum of surviving substructures, and this mix affects not only lensing, but also the stirring of the hot gas and the generation of weak shocks and wakes that have been observed as faint edges and ripples. The outer boundary of the halo is often discussed in terms of a virial radius, a scale inside which kinetic and potential energies obey a relation that indicates a quasi-equilibrium. Another operational boundary, the splashback radius, locates the outermost apocenter of recently accreted material and appears as a steep drop in the density of galaxies. These boundaries do not mark sharp edges in the dark matter. Instead, they define transitions in orbital history and in the phase space structure of the halo. In Abell 1, 2, 0, 1, the location of these transitions inferred statistically from the galaxy distribution and from weak lensing gradients is consistent with ongoing growth along preferred directions. Within these broad limits, the radial density profile declines gradually, and when scaled by the characteristic radius, it resembles profiles seen in numerical experiments that build halos through hierarchical merging. Concentration, a measure of how centrally peaked a halo is compared with its virial extent, connects to the formation time of the system. Through broad trends, earlier forming halos tend to be more concentrated. The concentration inferred for Abell 1, 2, 0, 1 falls within the typical range for massive clusters at similar distance once traxiality and projection are considered, indicating a formation path neither exceptionally early nor unusually late relative to peers of similar mass. Mass modelling introduces additional well-understood degeneracies. The mass sheet degeneracy in lensing allows a uniform sheet of mass to be added without altering shear, so absolute normalization benefits from magnification measurements or from combining shear with other probes. Stellar velocity analyses must contend with the unknown orbital anisotropy, for which flexible parameterizations and higher-order moments help. Hydrostatic masses must consider non-thermal pressure and clumping. Each method alone contains uncertainties, but their combination reduces the allowed range and exposes tensions if assumptions fail. In practice, for Abell 1, 2, 0, 1, the joint modelling across these methods yields coherent halo mass profile that rises more steeply than the gas density profile and declines more slowly than the number density of bright galaxies. a familiar hierarchy that reflects how different components respond to the same gravity. The geometry of the halo also leaves statistical fingerprints in the alignment of satellite orbits and in the shapes of isodensity contours derived from lensing. Satellite distributions tend to elongate along the major axis of the halo, and the diffuse intracluster light often shares this orientation, tying the shape of the luminous component to the shape of the dark skeleton. The hot gas, although rounder because of pressure, forces still follows the same broad axis, reinforcing the picture of a shared anisotropic potential. Over time, the halo grows through the steady addition of matter from the surroundings, and through occasional larger events when a substantial group falls in. Each episode adds energy and angular momentum to the system, and while relaxation and phase mixing erase many local details, some memory remains in the orientation and in the substructure spectrum. The current state of Abell 1201 therefore represents a snapshot in this long growth, with a mass distribution that is smooth on large scales, dimpled by small subhalos, and aligned with the filaments that deliver fresh material. At the cluster scale, this dark framework sets the stage for all other components, establishing escape speeds, sculpting the pressure support of the intracluster medium, and bending light from far beyond into arcs and shears that trace the otherwise unseen. By reading these combined signatures with attention to geometry projection and non-thermal effects, observers recover a quantitative map of the total mass that does not rely on light from any single component, and that respects the slow gravity-driven assembly of structure on the largest bound scales. The brightest cluster galaxy at the center of Abell 1-2, 01 presents a vast smooth stellar halo whose light fades gradually into the surrounding intracluster glow, and at this scale the object is best understood as a diffuse elliptical body with an extended envelope that carries the accumulated record of many past mergers. The outer isophotes, which are the lines of equal brightness on the sky, appear only slightly elongated and align with the broader axis of the cluster potential, a sign that tides and anisotropic accretion have shaped the galaxy in step with its environment. Surface brightness declines steadily over hundreds of thousands of light years, and the profile is well described by a high index curve often used for elliptical galaxies, but with an extra gently sloping component at large radii that observers call an envelope or CD halo. This outer component blends into the intracluster light so that there is no hard edge between galaxy and cluster, only a change from the brighter, more centrally bound stars to the faint sea of stars that orbit in the cluster potential. The starlight is dominated by an old metal-rich population typical of massive ellipticals, and color maps show a mild gradient in which the light becomes slightly bluer, with increasing radius consistent with a mix of stars that were formed in smaller progenitors and later deposited in the outskirts by tidal stripping and minor mergers. Subtle features sometimes appear at very low surface brightness. Broad shells, diffuse streams, and asymmetric plumes that trace the long, slow settling of accreted material. These structures are faint because the stars are dispersed over wide areas, but they persist for many orbital periods and record the geometry and timing of past encounters. The luminosity density implied by the smooth main profile falls quickly with distance from the center. Yet even a low density of stars integrated over such a large volume produces a substantial fraction of the total light, so the envelope is not a trivial addition, but a major store of baryonic mass. Kinematics on these scales reveal that the outer halo stars move in a potential that is already dominated by the cluster dark matter, rather than by the stellar mass alone, a fact reflected in velocity dispersion profiles that decline only gently with radius, or even remain roughly constant across large distances. The transition from galaxy-dominated gravity to cluster-dominated gravity therefore occurs well beyond the bright core and is written into the motions of the envelope. Planetary nebulae and integrated light spectroscopy serve as tracers of these motions in many systems, showing a mix of orbits and a slow change in angular momentum with radius that suggests the outer parts are assembled from material with varied origins. At the same time, the diffuse intracluster light shares similar colors and kinematics to the very outer envelope, reinforcing the idea of a continuum rather than a boundary. The stellar mass-to-light ratio for such an old population is high, compared with star-forming disks, and within the main body, the stars provide a significant fraction of the baryonic mass, even though the total gravitational field is set by dark matter on large scales. Because the population is old, ongoing star formation contributes little to the light, and dust plays a minimal role, except perhaps in localized lanes left by minor accretion events. This clarity allows the surface brightness profile to be modeled with confidence across a wide dynamic range, returning structural parameters that describe how concentrated the light is and how extended the halo becomes. Those parameters for brightest cluster galaxies tend to be extreme compared with normal ellipticals, with larger effective radii and higher central concentrations, reflecting both the early rapid growth phases and the later addition of diffuse material through dry mergers that add stars without much new gas. The build-up of the envelope proceeds through dynamical friction, a process in which satellite galaxies lose orbital energy to the background of stars and dark matter and spiral inward over many billions of years. As they sink, their outer stars are removed by tides and settle into the common halo, while their inner cores can survive to small radii or dissolve more gradually depending on concentration and orbit. The present-day appearance of the brightest cluster galaxy is the result of many such events, with a wide range of mass ratios and trajectories integrated into a single smooth profile by phase mixing that spreads stars around complete orbits. Because this mixing takes time, the far outskirts retain the clearest ghostly signs of recent accretion, while the inner halo looks more regular. The distribution of stellar metallicity also carries this history. The centers of the most massive, brightest cluster galaxies are metal, rich, consistent with deep, early potential wells that retain the products of many supernovae, whereas the outskirts show lower metallicity, characteristic of stars formed in smaller systems that were later accreted. Spectral absorption features measured across the face of the galaxy can be translated into simple indicators of age and chemical composition, and they often show a slow, monotonic change with radius. These patterns, together with the light profile and kinematics, allow the construction of mass models that include a luminous stellar component with a spatially varying mass-to-light ratio and a smoother, more extended dark matter halo. On the largest radii still associated with the galaxy, the stars and the intracluster light are mixed in both density and motion, which means that any sharp attempt to count stars as belonging to one or the other is a matter of definition rather than physics. The practical approach is to define a region where the brightness and the kinematics are still consistent with a bound galaxy-dominated component, and to recognize that beyond this region, the stars behave as part of the cluster. Applied to Abell 1201, this framing explains why some maps draw very extended contours around the central galaxy, and others define a smaller core plus an intracluster envelope. Both choices are attempts to describe a continuum. Another diagnostic at the host galaxy scale comes from the shapes of the isophotes. If the light follows the potential, and the potential is slightly elongated, then the isophotes echo that shape. Small twists in the position angle with radius can indicate the superposition of components with different orientations, or the imprint of recent accretion, along a direction that does not match the inner body. Brightest cluster galaxies often show such twists, and they are most common where the envelope is strong again, pointing to the role of late accretion in setting the outer structure. The colour of the light also matters in a practical way. In redder bands, the contribution from young stars and dust is reduced, and the envelope stands out more clearly against the sky, enabling deeper measurements of profile shape and extent. With such data, the profile can be traced to very faint levels, sometimes many magnitudes below the brightness of the night sky, which is necessary to follow the envelope to its limits. Even at great radii, the starlight is smooth enough that it does not fragment into obvious clumps above the detection threshold, a sign that most of the accreted stars have had time to phase mix around the galaxy. On the other hand, where individual satellites are currently interacting, one can find locally enhanced brightness, or broad fans of debris that will in time dissolve into the background. The ensemble of these features measured at many angles gives a three-dimensional sense of how matter has arrived. In Abell 1201, the overall impression is of a central luminous body that is oversized for a typical elliptical embedded in a still larger faint halo, whose orientation and mild elongation match the cluster, with a set of low contrast streams and plumes at the limits of detection that betray ongoing minor accretion. The kinematics at tens to hundreds of thousands of light-years reflect a high-velocity dispersion rather than coherent rotation, consistent with a collisionless assembly in a deep potential. Inside this scale, still at the host galaxy level, the light grows brighter and the density of stars rises enough that dynamical friction becomes more efficient for any remaining massive satellites, accelerating their inward drift and feeding the continued building of the inner body. The picture at this scale is therefore one of a galaxy inseparable from its environment, with an envelope that grades smoothly into the intracluster light, a stellar population that is old and metal-rich in the core, and more mixed outside shapes and alignments that echo the cluster and motions that show the grip of the whole potential well long before reaching the truly inner regions. The stars that fill the brightest cluster galaxy in Abell 1201 belong mostly to an old population that forms in the early universe, and then ages quietly, and this population can be read through its colour, its spectrum, and the way these properties change with radius, while a second, more discrete component made of globular clusters serves as a long-lived tracer of the galaxy's assembly history across very large scales. A stellar population in this context means the collection of stars formed in a burst or over a short interval, with similar age and chemical makeup, where chemical makeup is summarized by metallicity, the fraction of elements heavier than helium. In massive ellipticals, the light is dominated by red. Evolved stars whose spectra show strong absorption lines from metals, a sign that the gas from which they formed had already been enriched by previous generations of stars. When observers map colour across the face of the galaxy, the light tends to be slightly redder near the centre and slightly bluer in the outskirts, a shallow gradient that reflects higher metallicity near the core and a larger share of lower metallicity, stars at large radius consistent with a picture in which the inner body forms early, in deep potentials, while the halo gains stars later from smaller accreted systems. Simple models that fit the average spectra in radial bins return ages of many billions of years almost everywhere, and a slow decline in metallicity with distance, while the relative strength of features associated with different elements hints at contributions from both core collapse and thermonuclear supernovae to the enrichment pattern. The initial mass function, which describes the mix of stellar masses at birth, may vary with environment in subtle ways, but within the uncertainties allowed by available data for distant systems, a mildly bottom-heavy form in the central regions, and a more standard form outside often provide acceptable fits for massive galaxies, and such trends are compatible with the idea that dense early star-forming episodes produced relatively more low-mass stars in the inner parts. Because the light from these old stars changes slowly with time, the colour and spectral indices mainly trace composition rather than ongoing age changes, and dust plays only a minor role, except where small amounts appear in lanes brought in by recent minor accretion. Against this smooth field of stars stands the system of globular clusters, which are compact gravitationally bound groups of many thousands to millions of stars that form in very dense conditions and survive for a Hubble time. Brightest cluster galaxies commonly host globular cluster systems numbering in the many tens of thousands, far more than in a typical spiral galaxy, and their spatial distribution extends far into the halo, overlapping the domain where starlight fades into the intracluster background. The colours of globular clusters in massive ellipticals often show a bimodal pattern, with a blue group that is more metal-poor and a red group that is more metal-rich. The blue clusters tend to be more extended spatially, and are thought to include many members formed in smaller systems that were later accreted, while the red clusters are more concentrated and track the stellar mass of the main body, more closely suggesting formation in deeper potentials early in the history of the host. In Abell 1201, the expectation from comparable systems is a wide, nearly spherical or mildly elongated globular cluster envelope that follows the orientation of the galaxy, and the cluster with number density declining gently with radius, and with a higher fraction of blue clusters in the outskirts. Kinematics of globular clusters measured from spectra of individual clusters, where feasible, add another dimension. The velocity dispersion of blue clusters typically remains high at large radius, and can trace the transition from galaxy-dominated to cluster-dominated gravity, while red clusters show somewhat lower dispersions and a stronger connection to the stellar body of the galaxy. Subtle rotation may appear in one or both populations, often aligned with the photometric major axis. When present, this rotation provides clues to the net angular momentum deposited by past mergers. Because globular clusters are compact and bright compared with single stars at the same distance, they serve as excellent tracers out to very large radii, reaching well beyond the limit where integrated starlight can be measured with good precision, and their motions therefore help to map the gravitational field in the envelope, where the total mass is rising steeply with radius. The number of globular clusters per unit galaxy light, known as specific frequency, tends to be especially high for brightest cluster galaxies, reflecting the combination of early intense cluster formation and the later accretion of globular-rich satellites. Intracluster globular clusters, which are no longer clearly bound to any single galaxy, populate the cluster potential and blur the edge between the galaxy's system and the wider environment. Their presence further supports a growth path in which stripping and mergers redistribute long-lived star clusters across the node. Sizes of individual clusters measured as half-light radii increase with distance from the center. In many massive systems, a trend linked to weaker tidal fields and to the origin of many outer clusters in lower mass progenitors. The luminosity function of globular clusters, which describes how many appear at each brightness, shows a characteristic peak that serves as a standard candle for distance estimates when calibrated, and counts in Abell 1. 201 would be expected to follow this familiar form after correcting for observational completeness, allowing a self-consistent cross-check of distance and a census of the total population. The connection between globular clusters and the diffuse stellar halo emerges also in color and spatial correlation. Red clusters concentrate where the stellar light is denser, and share similar colors to the inner population, while blue clusters align with the extended envelope and resemble the metal-poor stars that are deposited in the outskirts by the shredding of smaller galaxies. In very low surface brightness maps, diffuse streams of stars can coincide with slight overdensities of globular clusters, marking recent accretion paths that have not yet phase mixed. Over longer times, those details fade, but the broad dichotomy remains as a fossil record, a concentrated metal-rich component linked to early deep collapse, and a widespread metal-poor component linked to later assembly from many lower mass units. Ultra-compact dwarfs, which sit at the boundary between the most massive globular clusters and the smallest galaxies, sometimes appear around brightest cluster galaxies and may represent the dense nuclei of larger satellites stripped of their outer stars. Their presence, if confirmed, adds another clue to the intensity of tidal processing near the center, and provides bright kinematic traces that reach small radii, though their detailed origin can vary from case to case. Beyond the clusters, other discrete traces such as planetary nebulae and bright red giant stars, when detectable, trace the same broad gradients and motions as the integrated light and the red cluster population in the inner halo, extending the reach of stellar kinematics into regions where spectroscopic measurements of the diffuse light are difficult. Chemical abundance ratios measured from integrated spectra of the main body, such as the ratio of alpha elements to iron peak elements, often remain elevated compared with solar values, which indicates rapid early star formation that ended before many thermonuclear supernovae enriched the gas with iron. This pattern supports a picture in which the core grew quickly and then faded while the halo assembled through many later additions that brought in lower metallicity stars formed over longer times. Each of these lines of evidence taken separately contains uncertainties from projection, from the blending of populations along the line of sight, and from the limited signal in the faint outer parts. Together, however, they form a consistent view of the stellar content at the host galaxy scale, a very old, mostly passive population with mild radial gradients in composition, a vast system of globular clusters that bifurcates into extended metal, poor and more concentrated metal-rich groups, and a mixing zone at large radii where the stars of the galaxy and the stars of the cluster potential become indistinguishable. In Abell 1201, this combined stellar record complements the light of the intracluster medium and the map of the dark matter halo to describe a central galaxy that has grown through both early rapid assembly and long slow accretion, leaving durable traces that can be counted, mapped, and where bright enough weighed by their motions across a span of hundreds of thousands of light years. The starlight profile of the brightest cluster galaxy in Abell 1.2, 01 provides a direct map of how visible matter is arranged, and careful measurements of that profile combined with modest and well-stated assumptions allow an estimate of how much stellar mass sits at each radius, and how that mass compares with the total gravitational field inferred from independent means. A surface brightness profile is simply the brightness of the galaxy as a function of distance from the center, measured in concentric elliptical rings that follow the shape of the isophotes, which are lines of equal light. Observers build this profile by masking foreground stars and background galaxies, subtracting the sky with high precision and averaging the remaining light at each radius. Because the envelope of a brightest cluster galaxy is extremely faint, at large distances the accuracy of the sky subtraction sets the limit on how far the profile can be followed. In deep images, the light falls smoothly over hundreds of thousands of light years, and the ellipticity and position angle remain nearly constant, with only gentle twists a sign that the luminous body is well aligned with the broader potential. To turn light into stellar mass, one multiplies the brightness by a mass-to-light ratio, which depends mainly on the age and metallicity of the stars, and on the initial mass function that sets the share of low-mass stars. In practice, the ratio is estimated by fitting the measured colours or spectra to simple population models that return an age and a metallicity, and then reading off the implied conversion between luminosity and mass in the observed band. Because colour becomes slightly bluer with radius in this galaxy, the mass-to-light ratio also falls gently outward, and applying a single constant ratio would overestimate the stellar mass in the outskirts. A radially varying ratio therefore yields a more faithful map of stellar mass surface density. Deprojecting the two-dimensional light into a three-dimensional luminosity density introduces geometric choices. A common approach assumes the galaxy is an oblate or triaxial ellipsoid with the observed axial ratio and projects a smooth three-dimensional profile that when reprojected matches the observed surface brightness. The exact shape along the line of sight is not uniquely known, but families of models with modest elongations produce similar luminosity densities when constrained by the observed isophotes and by the absence of sharp features. These models deliver a volume density of stars that declines steeply from the centre and then more gradually in the extended envelope. Integrating this density yields the enclosed stellar mass as a function of radius, and the curve rises rapidly in the inner tens of thousands of light-years before turning into a slower climb as the envelope adds mass over very large volumes. The cumulative stellar mass in the envelope is significant despite the low surface density because the area is so large. Photometric decompositions that try to separate a compact core from a broad outer component find that a single high-index profile cannot capture the full shape, and introducing an additional shallow component improves the match. This second component represents the CD envelope, which dominates the light at very large radii and connects to the intracluster light without a hard boundary. In redder bands, the envelope stands out more clearly against the night sky, and multi-band fits that allow the mass-to-light ratio to change with radius show that the mass fraction in the envelope remains high even after correcting for the bluer colour outside. A further refinement comes from two-dimensional fitting of the full image, rather than only the radial average. By modelling the galaxy with elliptical isophotes that can change ellipticity and position angle with radius, and by allowing a mild boxiness or diskiness in the isophote shape, observers capture subtle asymmetries that hint at the history of accretion. Residual maps, after subtracting the best-fitting smooth model, reveal low-contrast shells and streams that add only a small fraction of the total light, but carry clear information about recent additions. These features are strongest at the faintest levels and require careful treatment of scattered light and instrumental backgrounds to confirm. Stellar mass maps built from color-based mass-to-light ratios then combine with the structural model to yield a two-dimensional mass surface density that can be compared with the projected distribution of total mass at the same scale. Where the starlight drops more quickly than the total mass dark matter must account for a larger share of the gravitational field. Where the starlight remains comparatively strong, stars provide a larger fraction of the local baryonic mass. In the inner body of this galaxy, the stars contribute a large part of the baryonic mass budget, but the total field already shows the influence of the extended halo, and the fraction of mass in stars declines outward. This picture matches expectations for a central giant in a deep potential, a dense inner region where the luminous mass matters grading into a broad domain where the total mass grows more by the addition of unseen matter than by starlight. Color gradients provide an internal check on the adopted mass-to-light variation. If the gradient reflects metallicity more than age as indicated by spectral indices that show only mild changes in age-sensitive features, then a smooth decline in mass-to-light ratio is appropriate. If small pockets of younger stars exist, they appear as localized color deviations or dust lanes, and are masked or modeled separately to avoid biasing the radial trend. The global mass-to-light ratio within a chosen aperture can then be quoted with an uncertainty that accounts for model choices, photometric errors, and the unknown exact form of the initial mass function. Another route to stellar mass uses stellar population synthesis, anchored by spectral absorption features rather than broad-band colors. Where signal permits spectra in radial bins, constrain metallicity and abundance ratios more directly, and reduce degeneracy between age and metallicity. Applying this approach to the inner tens of thousands of light-years yields a slightly higher mass-to-light ratio than color, based fits alone consistent with a mildly bottom-heavy form of the initial mass function in the densest regions, while at larger radii the values converge toward those expected for an old metal-poor population formed in lower mass progenitors. The net effect on cumulative stellar mass is a steeper inner rise and a shallower outer tail than would be inferred with single constant ratio, but the total within the main body remains robust to these reasonable choices. Structural parameters derive from the light aid in comparing this galaxy to peers. The effective radius, which encloses half of the total light of the fitted model, is very large, while the profile shape parameter is high together, placing the object among the most extended known ellipticals. The extra light at large radius beyond what a single component would predict correlates with measures of local density and with markers of past interactions supporting the link between envelope strength and a long history of dry accretion. Despite these additions, the central brightness profile remains smooth and lacks a strong cusp, a trait often seen in massive ellipticals where a scouring by orbiting black holes during past mergers depletes the very center of stars and leaves a shallow core. Photometry at the resolution relevant here cannot resolve the innermost parsecs, but the absence of a sharp rise at the smallest radii accessible is consistent with a core-like structure on kiloparsec scales. All these photometric and population-based inferences carry known sources of uncertainty. Sky subtraction sets the floor for the outer profile. Deprojection depends on assumed geometry. The mass-to-light ratio hinges on simple population models that compress complex star formation histories into a few parameters. Yet when treated with care and cross-checked in multiple bands, the starlight profile remains a powerful direct tracer of the visible mass. In Abell 1201, the outcome is a luminous mass distribution that peaks strongly in the center, rolls over into a very extended envelope with a slowly declining mass density, and contributes a large but not dominant share of the total gravitational field beyond the inner body. This map of stars sets the stage for any analysis that seeks to separate the roles of luminous and dark components at the host galaxy scale, and it establishes a baseline against which independent constraints on the gravitational potential can be compared without invoking details from smaller radii or from phenomena that belong to deeper zones. Strong gravitational lensing turns the central region of Abell 1201 into a natural optical device that magnifies and distorts the image of a more distant galaxy, and the geometry of this effect encodes the inner gravitational potential of the lens with high precision. In simple terms, mass bends light, and when a background source, the lens galaxy, and the observer are well aligned, light from the source follows multiple curved paths around the lens, and arrives as several images on the sky. Where the surface mass density of the lens crosses a threshold set by distance ratios among observer lens and source, the mapping between source plane and image plane becomes singular along curves called critical lines. In the source plane, the corresponding curves are called caustics. A small source that lies near or across a caustic is highly magnified and stretched into an arc or split into multiple images whose positions and shapes are governed by the local gradient and curvature of the lensing potential. In the case of Abell 1201, deep images reveal a bright arc at a moderate radius on one side of the brightest cluster galaxy and fainter features that complete a partial ring-like configuration, while still fainter light appears closer to the center as a counter-image all produced by one background source whose light has been deflected by the central mass. The arc provides the first most obvious constraint. Its radius on the sky sets an approximate scale for the projected mass enclosed within that circle, because the Einstein radius of a lens depends on the square root of the enclosed surface mass density relative to a critical density defined by the lens and source distances. The more precise locations, widths and curvatures of distinct arc segments add further constraints on the gradient of the potential and on any ellipticity or external shear that distorts the symmetry. External shear in lensing means the tidal effect of mass outside the main lens that stretches images along a preferred axis, and in a cluster core this shear naturally arises from surrounding galaxies and the cluster halo. The relative brightness of multiple images of the same knot in the source gives magnification ratios that respond to small-scale changes in the second derivatives of the potential and can be perturbed by substructure. The detection of a faint counter-image close to the center adds special leverage. Such an inner image forms only when the source falls in a region of the source plane that maps through the inner caustic, and its location relative to the center and to the outer critical line depends sensitively on the slope and concentration of the inner mass profile. In practice, observers model the lens by representing the mass as a combination of smooth components and small perturbers. A smooth component may follow an elliptical profile motivated by halo models for the dark matter and by the measured starlight for the luminous mass, while small perturbers account for nearby cluster members whose halos locally distort the light paths. Each component has parameters such as central density scale radius, ellipticity orientation, and for galaxies a mass-to-light ratio that ties luminous light to mass. The model computes the predicted deflection field and maps the observed image plane pixels back into the source plane. A good model maps all multiply imaged features to a consistent compact source shape and reproduces the observed positions and relative magnifications when mapped forward again. Because the lens and source lie at known redshifts, distance ratios are fixed, and the solution space narrows to the distribution of mass in the lens. The presence of a counter-image near the center requires that the inner potential allow 3 or more images, which in turn restricts the inner slope of the projected mass. If the core of the mass were too shallow, or included a large flat density core, inner images would be suppressed or pushed to radii inconsistent with the data. If the inner slope were too steep without a concentrated central component, the mapping would place the inner image at a location or with a magnification that does not match the observation. In addition to positions and fluxes, high-resolution images can reveal small sub-features along the arc, such as brightness peaks that correspond to star-forming knots in the distant galaxy. Identifying the same knots in different images tightens constraints by anchoring the mapping at multiple points. Spectroscopy of the arc fixes the source redshift, and can also provide velocity gradients across the source that must be mapped consistently by the model, further checking the deflection field. In the crowded core of a cluster line of sight, structures add weak additional deflections that are usually treated as a small effective convergence and shear. But careful work allows for this by marginalizing over reasonable ranges, or by including explicitly the nearest projected perturbers with measured redshifts. Several degeneracies are known and must be addressed. The mass sheet degeneracy allows a uniform sheet of surface density to be added, while rescaling the source, leaving image positions unchanged, but shifting absolute magnifications. Joint use of weak lensing and stellar kinematics helps to break this degeneracy by fixing the normalization of mass at larger and smaller radii. The ellipticity of the smooth halo and the strength of external shear can trade off to some degree, but the full two-dimensional shape of long arcs and the relative angles between arc segments constrain this trade enough that only a narrow band of combinations fits. Substructure near an image can alter its brightness without greatly moving its position, an effect that introduces some freedom in matching flux ratios. Models treat these as nuisance parameters or as an opportunity to count and weigh subhalos if data are rich. Pixel-based source reconstructions reduce bias from assuming a simple source shape. In this approach, the source plane is divided into small elements whose intensities are solved for simultaneously, with lens parameters such that the forward-mapped image reproduces the observations with minimal residuals, given a regularization that favors smooth sources. The resulting source can be irregular, yet the lens must still place each pixel of the arcs consistently, which tightens constraints on the potential. For Abell 1201, the combination of an extended bright arc at tens of thousands of light-years and a very faint inner counter-image implies that the central projected mass rises steeply enough to produce two distinct critical curves, an outer tangential one that hosts the long arc, and an inner radial one that allows an image inside. The exact radii of these curves depend on the balance among the stellar mass of the brightest cluster galaxy, the dark matter cusp, and any additional very compact mass at the very center. The shape of the outer arc reveals that the potential is not perfectly circular but slightly elliptical, and influenced by nearby cluster members, a natural outcome in a dense environment. The modeling workflow tests families of inner mass profiles from those with shallow cores to those with steeper cusps and finds which ones reproduce both the outer and inner images without producing spurious extra images or missing observed ones. The goodness of fit is judged by how closely predicted and observed positions agree in angular terms, and by how well magnification ratios and image shapes are matched. Recognizing that small-scale substructure and micro-lensing by stars can perturb fluxes at the few tens of % level. When the model reproduces the full set of observables with a compact source consistent across all images, the inferred inner mass distribution follows as a byproduct. The mapping also predicts time delays between light paths, which are differences in travel time, caused by path length and gravitational potential. In a system without a variable source, these delays do not lead to measurable brightness changes, but they remain part of the consistent solution, and can be quoted as a check on the scale of the potential. Finally, uncertainties are estimated by exploring parameter space, with methods that sample the posterior probability-producing ranges for inner slope ellipticity, external shear, and enclosed mass within chosen radii. In sum, the strong lensing geometry of the arc and counter image in Abell 1.2 01 offers a detailed local probe of the inner gravitational potential that complements the broader lower resolution maps from weak lensing and the independent information from stellar light and gas, and by matching all images in position and shape within known degeneracies, it anchors the scale and the profile of mass in the central tens of thousands of light-years with unusually sharp focus. The faint counter-image seen close to the center of the brightest cluster galaxy in Abell 1.2 01 acts as a sharp lever on the inner mass distribution because such an image appears only when the mapping from source to lens plane crosses an inner caustic that exists for sufficiently concentrated central potentials. In practice, reproducing both the bright outer arc and the dim inner image requires a mass model whose projected density climbs steeply toward the center and then relaxes outward on the scale of tens of thousands of light years. If the inner profile were too shallow, the radial critical curve would vanish, and the counter image would not form. If the profile were too steep but spread out without a compact core, the predicted location and brightness of the inner image would be inconsistent with what is observed. Modelers therefore build families of lenses that include a luminous stellar component, with a radially varying mass to light ratio guided by measured color and spectra. A smooth dark halo with flexible inner slope and ellipticity, and a set of small perturbers associated with neighboring cluster galaxies. The unknown element is whether an additional very compact mass concentrated within the inner hundreds of light years is required to match the data, and the presence of the counter-image answers yes in a striking way. When a compact central mass is added, the inner potential deepens at very small radii, while leaving the larger scale gradient set mainly by stars and halo. The mapping then produces an inner image at the observed offset and with the correct parity, and it does so for a range of acceptable ellipticities and external shear values that reproduce the shape of the long arc. The amplitude of the compact mass term sets how far inward the inner critical curve moves and how bright the counter-image becomes. A small compact mass leaves the inner image either too bright or in the wrong place. A very large compact mass crushes the inner caustic or drives the outer geometry off. Between these extremes lies a narrow range in which the model crisply matches both inner and outer features. Translating the compact mass into a physical interpretation favors a central black hole, because no other long-lived component can carry so much mass within so little space. The implied mass lies on the order of 30 to 33 billion solar masses, when the stellar mass-to-light ratio follows the measured gradient and the inner slope of the dark halo remains within the range, allowed by numerical experiments for massive halos at this epoch. The exact value is model-dependent, and careful work reports not a single figure, but a credible interval that reflects uncertainty in geometry, in the stellar population parameters, in the degree of non-axis symmetry, and in the contribution from small perturbers. Even with these allowances, the requirement for a very large compact mass remains robust, because removing it degrades the fit abruptly in features that cannot be rescued by tuning other parts of the model. Several known degeneracies are handled explicitly. The mass sheet degeneracy is limited by anchoring the model to weak lensing and to the measured dispersion of stars at larger radii, which sets the overall normalization of mass beyond the strong lensing zone. The trade between halo ellipticity and external shear is reduced by using the full two-dimensional arc morphology, so that not only image positions but also their curvature and relative orientation are matched. Substructure near the arc can alter brightness ratios, yet the position of the counter-image is insensitive to such small perturbers, and the model does not rely on precise fluxes to claim the compact mass. Source structure degeneracy is addressed by pixel-based reconstructions that do not force the background galaxy to be a single smooth ellipse. The model is asked to map irregular features consistently across images, and failure to do so signals an incorrect potential rather than a poor source guess. Projection effects and triaxiality are explored by allowing the main halo to be elongated along the line of sight, or across it within sensible limits. These changes nudge the best-fitting compact mass but do not remove the need for it. Gradients in the stellar mass-to-light ratio are crucial. If a single high ratio is forced throughout, stars account for too much mass at intermediate radii and too little close in, and the predicted counter-image shifts or dims incorrectly. If a single low ratio is used, the model compensates with a steeper halo cusp that spoils the arc shape or drives the inner image away from the observed site. Allowing the ratio to decline gently with radius as suggested by color and spectral indicators restores balance. Stars dominate the luminous mass in the inner body without overshooting at larger radii. The halo supplies the slow outer gradient, and the compact term supplies the final inward spike that the counter-image demands. Stellar kinematics provide an independent cross-check. Although the sphere of influence of a black hole of this mass projects to an angular scale too small for direct resolution at this distance, the average dispersion of stars within apertures that cover the strong lensing region responds slightly to the extracentral gravity. When models that fit the lensing also reproduce the measured dispersion profile within uncertainties, confidence rises that the decomposition among stars' halo and compact mass is physically sensible. Conversely, models that remove the compact term tend to lean on unreasonably high stellar mass to light ratios or on halo slopes that contradict results from simulations and from other clusters, and they struggle to maintain agreement with the observed velocities. Systematic effects receive close attention. The precise center of the light distribution defines the lens origin. Small offsets can bias the inner image fit so the centroid is fixed by high signal images and its uncertainty is propagated. The point spread function of the imaging affects the detectability and shape of the counter-image. Models convolve predictions with the measured point spread function and test small variations. Line-of-sight structures contribute a weak, nearly uniform convergence and shear. These are marginalized over using estimates from galaxy counts and from cosmic variance at the measured redshift. Nearby cluster members are assigned mass following their light with a scatter that covers plausible mass to light ranges, and their halos are truncated at radii consistent with the crowded core. With all these ingredients varied, the posterior distribution for the compact mass remains peaked at values consistent with an ultra-massive black hole and excludes small values with high confidence. The conclusion emerges not from a single feature, but from the joint requirement that one model reproduce the outer arc positions and shapes the presence and location of the inner counter-image. The lack of spurious extra images, the modest external shear expected in a cluster core, and the measured gently declining stellar mass to light ratio. Within that joint requirement, the compact mass lands at a value that's among the largest ever inferred on the scale of several tens of billions of solar masses, and it does so without calling on exotic components beyond stars' dark matter, and a central object whose properties match a black hole. Uncertainties remain, and they are stated plainly. If the true inner halo were substantially steeper than most simulations predict for halos of this mass, the compact term could be somewhat smaller. If the central stellar population had an initial mass function even more bottom-heavy than the already high values favoured by the densest cores, stars could carry more mass and narrow the compact range. If line-of-sight convergence were higher than standard estimates, absolute masses would shift while relative decompositions would remain similar. Each of these paths has limits grounded in data and theory, and none erases the core result that a concentrated nearly point-like mass is required by the lensing geometry. In this way, the counterimage serves as a direct local test of the innermost mass, and the strong lensing model built with measured light, flexible but realistic halos, and explicit small perturbers converts that test into a quantitative estimate of a central mass on the order of 30 to 33 billion solar masses with clearly marked model dependencies and error bounds that reflect what the data demand and what they allow. Stellar motions in the inner body of the brightest cluster galaxy in Abell 1-2. 0-1 provide a direct local measure of the central gravitational field because the random speeds and any ordered rotation of the stars respond to the mass enclosed within each radius. The primary observable is the velocity dispersion, the spread in line of sight speeds inferred from the broadening of absorption lines in the integrated spectrum of old metal-rich stars. A high central dispersion that declines only gently with radius indicates a deep potential well whose gradient changes slowly across the inner tens of thousands of light years, while subtle departures from a smooth decline point to changes in orbital structure or to additional mass components. Two-dimensional integral field spectroscopy maps this dispersion over many small spatial elements, at once returning not only the luminosity-weighted dispersion, but also the mean streaming velocity and higher-order shape parameters of the line-of-sight velocity distribution that are sensitive to skewness and kurtosis. These higher moments help to distinguish between different mixtures of orbits, because radial orbits and tangential orbits project differently along the line of sight and imprint different asymmetries and wing strengths on the absorption features. Extracting these quantities requires careful attention to instrumental resolution, to the point spread function that blends light across neighbouring elements, and to the choice of stellar templates whose metallicity and abundance ratios match the galaxy's population. Each of these affects the measured widths at the few percent level, and therefore the inferred mass at small radii. Modelling translates these maps into a mass profile through the collisionless Boltzmann equation, which governs how a steady population of non-colliding stars occupies a gravitational potential. One widely used reduction is the Jeans approach, which relates the intrinsic dispersions and anisotropy of orbits to the enclosed mass, once the deprojected stellar density is supplied by the photometry. A more flexible route assembles superpositions of many representative orbits in a trial potential and adjusts their weights to reproduce simultaneously the surface brightness and all measured kinematic moments. This orbit-based method allows for general anisotropy patterns and for mild triaxial shapes, which matter in massive ellipticals where perfect axial symmetry is rare. In both routes, the luminous stellar mass profile enters through a mass to light ratio that can vary with radius, in the way implied by measured colour and spectral gradients, while the dark halo contributes a slowly varying background over the inner field of view. Finite angular resolution is a central limitation at the distance of this cluster. The projected radius within which a very compact central mass would dominate individual stellar orbits is far smaller than a typical seeing disk, so no single spaxel isolates that domain. Even so, extracentral gravity still alters the luminosity-weighted dispersion measured in small apertures, and its signature can be recovered statistically by forward modelling that accounts for the point spread function and for the exact placement and size of the apertures. In practice, the model produces predicted kinematic maps by convolving intrinsic fields with the point spread function, and comparing those predictions to the observed maps across all spatial elements, so that the influence of compact central gravity, extended stellar mass, and the dark halo are constrained together rather than one at a time. The choice of stellar templates introduces an additional source of bias, if not handled carefully, because old metal-rich populations display strong absorption features whose depths depend on abundance ratios as well as on metallicity. Modern fits solve simultaneously for kinematics and for a flexible combination of templates that span the likely range of ages and compositions, limiting the risk that a mismatch masquerades as a change in dispersion. Where faint emission lines from warm gas are present, they can partly fill absorption troughs and artificially narrow the fitted profiles unless modelled. Masking or simultaneous emission line fitting prevents this. The measured maps in massive brightest cluster galaxies commonly show very weak rotation compared with dispersion consistent with an assembly dominated by many dry mergers that scrambled angular momentum. When rotation is present, it often aligns with the photometric major axis and rises only slowly with radius. The dispersion field peaks near the center and falls gently outward sometimes with low contrast plateaus, or ripples, associated with changes in orbital anisotropy, or with the transition between a compact inner body and a more extended envelope. The higher moments reveal whether the orbits are more radial or more tangential. A pattern in which the fourth moment is positive toward the center suggests more radial motions along the line of sight, while negative values indicate a preference for tangential motions in projection. These trends constrain the anisotropy parameter that compares radial and tangential dispersions, and in turn they limit the family of mass profiles that can reproduce the data. In the inner body of this galaxy, the old stellar population and the smooth light profile imply a relatively featureless gravitational field, except for the steady inward rise expected from the luminous mass and any additional concentrated mass at very small radii. The dark halo contributes a gently varying background over these scales, so its main role is to fix the slope of the potential near the outer edge of the kinematic field, rather than to supply a sharp central spike. When the model adopts a radially varying stellar mass-to-light ratio that declines from the metal-rich center to the slightly bluer outer body, the stars account for a large share of the gravity within the inner tens of thousands of light-years without overshooting at larger radii. If instead a single high ratio is forced throughout the model, tends to predict too much mass at intermediate radii, and cannot match the measured decline of dispersion without invoking an orbital structure that is strongly tangential in an unphysical way. If a single low ratio is imposed, a steeper dark halo cusp must compensate, and the fit degrades because such a cusp bends the dispersion profile too quickly and conflicts with expectations from larger scale constraints. Aperture definitions matter, because past measurements often report dispersions in circular or elliptical apertures that do not match the spatial sampling of integral field data. To compare or to combine constraints, one integrates the modelled kinematic field over the exact apertures used by each instrument and over the same weighting by surface brightness, then adjusts the model parameters to satisfy all measurements at once. This procedure ensures that the inner profile is anchored by the small aperture dispersions, while the outer slope is set by larger apertures and by the decline seen across the map. Deprojection adds geometric uncertainty, because the intrinsic three-dimensional shape and the viewing angle are not known a priori. Orbit-based models address this by exploring axis-emmetric and mildly triaxial families, whose projected isophotes match the observed ellipticity and its slow twist with radius. Acceptable shapes yield similar enclosed mass profiles when constrained by the same kinematic data, and the remaining spread is included in the quoted uncertainties. Random errors arise from finite signal to noise and from template variance, while systematic errors come from point spread function, characterization, sky subtraction in the outer bins, and the assumed functional form of the mass-to-light gradient. Tests that vary each of these within reasonable bounds change the normalization of the stellar mass modestly, but leave the qualitative shape of the mass profile intact. Taken together, the two-dimensional dispersion field, the weak rotation and the higher moments are reproduced by dynamical models in which the luminous stellar mass dominates the inner gravitational field. The dark halo supplies a nearly constant background over the field, and an additional concentrated central contribution is allowed within the limits of spatial resolution without being interpreted beyond the scope of this layer. The emphasis at this stage remains on how the measured motions map the inner tens of thousands of light years, and how the combined data restrict the allowed combinations of stellar mass profile, orbital anisotropy, and smoothly varying halo, establishing a consistent observation-anchored description of the gravitational potential over the inner kiloparsecs that prepares without previewing details for deeper analyses that lie still further inside. Within the inner kiloparsecs of the brightest cluster galaxy in Abell 1-2, 0-1 gravity changes character from the broad, gently varying pull of stars plus halo to a steep central field set by a compact mass, and this change defines a practical boundary often called the sphere of influence, the region where the additional attraction from the central object dominates the random motions of nearby stars. For an ultramassive black hole with a mass of several tens of billions of solar masses embedded in a dense hot stellar body whose velocity dispersion is a few hundred kilometers per second, that boundary spans roughly a kiloparsec scale, meaning thousands of light years, so the influence reaches well beyond the tiny horizon that belongs to the relativistic regime and shapes the dynamics of a substantial inner volume. Inside this zone, the distribution of stellar orbits reflects the central spike in potential. If the galaxy assembled through repeated dry mergers, the orbital families that remain after long mixing tend to avoid the very center. In a mild way, a signature of scouring by past black hole pairs that removed stars on the most radial paths and left a shallow core in the brightness profile across the inner kiloparsecs. The present-day field then guides stars on orbits with a more tangential bias, at the smallest radii a bias that helps keep the innermost light smooth rather than cuspy. Two-dimensional maps of the line-of-sight velocity distribution in such regions once corrected, for the point spread function, show a high dispersion with only gentle spatial gradients and weak rotation, a pattern that is consistent with a pressure-supported system where local speeds rise toward the center under the pull of the compact mass but are averaged over many directions. The timescales for stars to exchange energy through close encounters in this dense yet vast environment remain far longer than a Hubble time, so the stellar system evolves collisionlessly. Phase space is populated by orbits set by the smooth potential rather than by frequent stellar encounters, and the structure is stabilized by the integral constraints of conserved energy and angular momentum. Within the inner kiloparsecs, the luminous density rises steeply toward the center, before flattening into a shallow core, and this shape can be measured even at moderate resolution by fitting the surface brightness with core-type models that transition from a gentle outer slope to a nearly constant central brightness over a finite scale. The size of this core records how far past scouring penetrated and links indirectly to the history of central black hole pairs that formed during mergers of predecessors. The present ultramassive object deepens the potential well without substantially altering the visible core shape on kiloparsec scales, because the stars respond as a collisionless ensemble and the light is already smoothed by many orbits. Kinematically, a central rise in the luminosity-weighted dispersion across small apertures is the clearest local sign of the compact mass in this regime. Models that include a radially declining stellar mass-to-light ratio, a smoothly varying dark halo, and a central point-like term reproduce a dispersion field that peaks gently toward the center, while remaining compatible with the slower decline seen across the inner kiloparsecs. If the point-like term is removed, the same models must force either an unphysically high central stellar mass-to-light ratio or an inner halo slope that is too steep to agree with constraints at larger radii, and the predicted dispersion field bends away from the observed pattern. The geometry of the potential inside the sphere of influence also shapes how orbits fill space. Box-like orbits that pass near the center are more easily depleted when a central mass grows, leaving a higher fraction of tube orbits that circulate with a preferred sense around the symmetry axis and avoid the very center. In projection, this shift in orbital mix appears as a subtle dip in the fourth moment of the line-of-sight velocity distribution toward negative values near the center, signaling a more tangential bias, while at larger radii the moment rises toward values that admit more radial motions. Such patterns, when seen with adequate signal and modeled with orbit-based methods, point to a dynamical structure in which the compact mass enforces central roundness in velocity space, even if the global shape remains slightly elongated. The dark halo contributes a nearly constant background acceleration across these inner kiloparsecs, and thus sets the outer boundary conditions for orbits, but does not create a sharp central gradient. The luminous stars create the main rise in the potential from several kiloparsecs inward. The compact term adds the final steepening inside a kiloparsec. This layered composition explains why the dispersion profile responds smoothly, rather than with a sudden jump. Stellar populations in this region are old and metal-rich, and the color gradient that runs from redder in the innermost arcseconds to slightly bluer outside implies a mass-to-light ratio that declines gently with radius. Incorporating this gradient reduces the need to ascribe excessive mass to stars at intermediate radii, and it allows the compact term to account for the extra central pull without conflict. The same gradient ensures that the enclosed stellar mass within a kiloparsec is large but not overwhelming, compared with a compact mass, so the sphere of influence remains a broad domain rather than a knife edge. Dust is sparse in this region, in massive passively evolving ellipticals, and when present it appears as narrow lanes or patches that can be masked during kinematic extraction and photometric modelling. Their removal keeps the derived central light and dispersion free of artificial dips or spikes. Cold gas is likewise scarce, and where small amounts exist they orbit or drift under the same potential without generating strong emission, indicative of rapid accretion, a point developed separately when discussing activity limits. With gas and dust playing minor roles, the central kiloparsecs offer a clean view of stellar dynamics under a combined potential that transitions from distributed to concentrated. The gravitational field in this zone also sets the stage for tidal interactions between stars and the central mass. A star wandering too near can be tidally disrupted if its closest approach falls within a characteristic radius that depends on its own size and on the mass of the black hole. But for the ultramassive regime, the disruption radius for a typical Sun-like star lies inside or near the event horizon. So many potential disruptions become direct captures without bright flares. This shift makes dramatic stellar feeding events rarer to observe in such systems, even though the lost cone, the set of orbits that would plunge deep enough to be swallowed, is not empty. The relaxation that refills the lost cone is inefficient at these scales, and the net rate of captures remains low on human timescales. Compact remnants such as stellar mass black holes and neutron stars can in principle sink deeper through dynamical friction than single stars, but the times required in a hot low-density nucleus at these radii remain very long, so their contribution to feeding is negligible in steady state. The shape of isophotes in the inner kiloparsecs offers an additional diagnostic of the potential. If the central mass were offset appreciably from the light centroid boxy distortions or isophote twists would appear at small radii. Observations of massive central ellipticals typically show smooth, nearly concentric isophotes, with only mild twists that continue trends seen outside, supporting the assumption that the compact mass sits at the photometric and dynamical center, to within the resolution of current data. Subtle departures that do occur can be attributed to faint dust lanes or to the projected influence of small satellites that pass nearby on the sky but do not disturb the core structure. In combination with strong lensing which probes comparable projected radii along specific sightlines, the stellar dynamics across the inner kiloparsecs fix the inner slope of the total mass profile and the normalization of the compact term. The lensing speaks through geometry, demanding a steep central potential to produce both a long tangential arc and a faint inner counter-image, while the dynamics speak through motions demanding that the same potential produce a high central dispersion without forcing implausible orbital anisotropies. Where these two independent lines agree within their respective uncertainties, confidence grows that the mass decomposition into stars' dark halo and compact object is reliable over this domain. The outcome for Abell 1-2. 0-1 is a coherent dynamical picture, a broad pressure-supported stellar system whose velocity dispersion stays high and falls only slowly over kiloparsec scales, a shallow core in the surface brightness that hints at earlier scouring, a gently declining stellar mass to light ratio that keeps the luminous mass from overshooting at intermediate radii, and superimposed on these a compact central mass whose sphere of influence stretches across thousands of light years and shapes the inner orbital architecture in ways that are measurable, even when the true relativistic boundary lies far below the resolution of current instruments. In this way, the inner kiloparsecs serve as both a laboratory for collisionless dynamics in a deep potential and as a bridge between global cluster-scale gravity and the concentrated field that rules the immediate surroundings of the central object, cold gas dust and any signs of nuclear activity in the central galaxy of Abell 1-2. 0-1 are constrained by observations that span optical infrared millimeter radio and high-energy bands, and together these limits point to a nucleus that accretes little material and shines weakly compared with its deep gravitational potential. In massive passively evolving ellipticals, optical spectra often show only faint or absent emission lines from warm gas. When lines are present, they tend to be low in excitation and narrow in width, indicating modest ionized gas masses and slow internal motions. Images sensitive to dust reveal in some brightest cluster galaxies narrow lanes or patchy structures that likely trace minor accretion of small satellites, but the total dust mass remains small compared with star-forming spirals, and the features do not extend far enough or shine brightly enough to imply vigorous feeding of the nucleus. Mid-infrared observations provide a complementary test for warm dust that would glow if a strong obscured central engine heated a surrounding torus. In cases like Abell 1201, the mid-infrared continuum is weak and lacks the strong rising shape expected from hot dust near an active nucleus, consistent with a low energy output. At millimeter wavelengths, searches for molecular gas use rotational lines of carbon monoxide as tracers. Many central ellipticals in non-cooling core clusters show non-detections or very small molecular reservoirs and upper limits at the distance and depth. Relevant here imply cold gas masses that are tiny, compared with the stellar mass insufficient to sustain significant accretion for long. Where small amounts of molecular gas are detected in similar systems, the gas often appears in compact clumps or short filaments, with low total mass and little associated star formation. Far infrared color ratios likewise indicate little recent star formation, and ultraviolet imaging returns smooth old stellar light rather than patchy young populations. The hot medium of the cluster adds another channel by which the central object could be fed, because gas that settles toward the center could in principle enter a spherical low-angular momentum flow from the ambient plasma. Estimating such a hot accretion rate requires the gas density and temperature near the gravitational capture radius, a scale set by where the thermal speed of the gas becomes comparable to the escape speed. Although that radius lies far below the direct resolution of current X-ray instruments at this distance, the broader profiles of density and temperature can be extrapolated inward with plausible gradients. These estimates return capture rates that are small in absolute terms, and when converted into an expected light output for a radiatively efficient disk, would predict luminosities far higher than observed. The natural conclusion is that if gas does reach the inner regions, it does so in a radiatively inefficient state, in which most of the gravitational energy remains as heat or kinetic energy in the flow, rather than emerging as light, keeping the observed brightness low even for non-zero inflow. Radio observations test for compact jets or cores powered by such low-efficiency accretion. In many massive ellipticals, weak radionuclei are detected with flat or slightly inverted spectra, and sizes below a kiloparsec, sometimes accompanied by tiny lobes that indicate intermittent outflows. The radio power in these objects lies orders of magnitude below that of classical radio galaxies, and fits a mode often called low excitation, or jet-dominated, in which mechanical energy transported by outflows may exceed the radiated power. In the specific environment of a cluster core, such mechanical feedback stirs the hot atmosphere, but the energy injection in systems without dramatic cavities remains modest. For Abell 1201 published constraints on compact radio emission and on extended structures allow only a faint core and no large lobes consistent with the nucleus that is active at a very low level. X-ray imaging of the inner region is dominated by diffuse emission from the intracluster medium whose brightness far exceeds any nuclear point source unless the nucleus is unusually bright. After modelling and subtracting the extended gas component, the remaining point-like emission at the centre is weak or undetected setting limits on the hard X-ray luminosity that fall well below what a radiatively efficient accretion disk would produce for even a small fraction of the Eddington rate, the benchmark at which radiation pressure balances gravity in a spherical flow. These limits agree with the low infrared and radio outputs and strengthen the case for a quiescent, radiatively inefficient state. The absence of strong, sharp X-ray cavities or bright radio bubbles near the core further suggests that any recent jets have been gentle and small, although it remains possible that older faintly mixed cavities exist below present detection thresholds. Optical and near-infrared integral field spectroscopy offers another handle on nuclear activity through the measurement of line ratios that diagnose ionization mechanisms. When emission is present in central ellipticals with weak nuclei, the ratios frequently fall in regions associated with heating by old hot stars or by low-level shocks rather than by a luminous active nucleus, and the line widths are narrow enough to be explained by gravitational motions in the central potential rather than by outflows. In Abell 1201, the expectation from analogous systems is that any such lines would be faint and spatially smooth on kiloparsec scales with no strong compact component at the centre. Polarimetric observations sometimes reveal hidden broad line regions in more luminous active galaxies through scattered light, but in low-power central ellipticals, these signatures are generally absent and upper limits again support a quiet nucleus. The combined multi-wavelength picture therefore shows consistency across independent measurements. Cold molecular gas is scarce, dust is present at most in small patches, star formation is negligible, mid-infrared signatures of hot dust are weak, compact radio emission is faint and X-ray point source limits are low. Each of these data sets contains uncertainties tied to depth subtraction of bright extended components and the risk of confusion with small satellites projected near the line of sight. Yet the pattern they form leaves little room for a luminous, radiatively efficient nucleus. Instead, the nucleus appears to reside in a state where inflow, if present, is meagre, and settles into a hot, thick, inefficient configuration, or is balanced by weak outflows that carry away energy mechanically, without producing strong radiation. Such a state meshes naturally with the old gas-poor stellar population, the long cooling times of the surrounding hot atmosphere at these radii, and the lack of strong cooling flow signatures like extended bright multiphase filaments. It also aligns with a general trend for the most massive central galaxies in non-cool core clusters to host weak maintenance mode activity rather than bright, rapidly accreting centers. Limits at finer scales remain model-dependent because the exact density and temperature structure near the capture radius is not directly measured, and because unresolved compact jets can hide mechanical power without much light. Nevertheless, the concordance of low infrared luminosity, low hard X-ray, luminosity faint or absent, optical emission lines, and only modest radio power constrains the allowed parameter space for any central engine tightly. If present, it must operate at a tiny fraction of the accretion rate and radiative efficiency that would produce a bright active galaxy, leaving the central regions dominated by the gravity of the compact mass rather than by its light. A central object can grow only by gaining mass, and it can shine only by turning a part of that infalling mass into light. So the quiet appearance of the nucleus in Abell 1201 sets strong boundaries on how matter moves through the inner region and how efficiently it radiates as it falls. Accretion in a gas-poor hot environment begins with capture from the surrounding plasma at a scale where the pull of gravity overcomes the thermal stir of the gas. That capture scale lies far outside the true relativistic boundary, yet far inside the kiloparsec domain mapped by stellar dynamics, and within it the gas must shed energy and angular momentum to continue inward. In a classical thin disk, gas cools, rapidly settles into a dense sheet, and radiates efficiently, but the weakness of optical ultraviolet and X-ray light from this nucleus argues against such a disk. A different state, often called a radiatively inefficient flow, fits the limits. In this mode, the gas remains hot and puffy, the ions carry most of the heat, and because collisions are rare, the energy stays with the flow, rather than turning into light and escaping. The material drifts inward slowly, more like a thick warm breeze than like a bright thin river, and much of it can be lost to gentle winds or weak jets before it ever reaches the last stable orbits. The expected signature at low rates is a faint compact radio core, weak or undetected hard X-rays, and little mid-infrared emission from hot dust, a pattern that matches what is seen or limited here. The rate at which the hot atmosphere can feed the center depends on the local density and temperature near the capture scale. Extrapolations from the observed cluster gas suggest densities that are very low and temperatures that are very high, so even the maximum hot inflow is small in absolute terms. If that small inflow were to shine with efficient conversion to light, it would exceed the limits by a wide margin, so the only consistent picture is one in which a large fraction of the energy remains trapped in the flow or is carried away mechanically. Magnetic fields thread the plasma and guide how angular momentum moves. In a hot dilute flow, the magneto-rotational instability can stir turbulence that transports angular momentum outward and lets mass move inward. At the same time, large-scale fields anchored in the inner flow can collimate a weak jet that carries energy and a trickle of mass outward. Such jets need not inflate grand cavities in the surrounding gas to matter. Even small intermittent puffs can heat nearby plasma and help keep cooling in check. the lack of strong symmetric radiolobes near the center of Abell 1-2. 01 does not rule out such activity. It sets an upper bound on how much time-averaged mechanical power the jet can carry without leaving bright marks. Polarization and rotation measure studies in central ellipticals elsewhere show that hot flows near massive black holes can be magnetized enough to shape the dynamics, yet not dense enough to produce large Faraday depths along the line of sight. By analogy, similar conditions are plausible here, consistent with the quiet radio appearance. Angular momentum at capture is another key. Gas drawn from the intracluster medium does not arrive with zero swirl. Even a small net spin can set a circularization scale inside which the flow tries to form a disk. In a radiatively inefficient state, that disk would be thick and patchy rather than thin and bright. If the nucleus also receives occasional small clouds from tidally stripped satellites, their angular momenta may cancel or add in irregular ways, leading to a flickering pattern of inflow in which the time-averaged rate remains very low. Variability on human timescales would then be modest in a distance-averaged view, because the time to cross the inner flow crosses many years to centuries, yet brief radio brightenings could occur when a clump reaches the innermost region and powers a small flare. The spectrum expected from such a flow peaks at long wavelengths, where self-absorption weakens the radiation only slowly with frequency. Toward higher energies, the spectrum falls without the strong blue bump that marks a thin disk. The weak mid-infrared continuum reinforces the lack of hot dust close to the engine, which would otherwise glow if a luminous inner source heated a torus. Together, these traits imply an Eddington fraction, meaning the ratio of actual light output to the limit, where radiation pressure balances gravity in a spherical flow that is tiny far below 1 part in 1,000. In this regime, the mechanical energy carried by a jet or by broad outflows can exceed the radiated energy, even though both are small. The surrounding hot gas responds to such gentle feedback by developing small sound waves, weak ripples or mild turbulence, rather than by carving large cavities, and the energy dissipates gradually as heat helping to offset slow cooling. The balance is delicate. If inflow rose briefly, the nucleus could become brighter and carve small bubbles that later buoy outward. If inflow fell, the nucleus would dim and the atmosphere would cool slightly faster, perhaps drawing in just enough extra gas to restore the previous state. Over very long times, this gentle self-regulation can maintain a low level of activity without dramatic events. On the path inward, the flow must pass through a region where electrons and ions may have very different temperatures because they share energy inefficiently in such a thin plasma. Ions carry most of the heat and approach near virial temperatures set by gravity, while electrons which radiate remain cooler and are responsible for the observed light. If the coupling between species is weak, most of the energy plunges inward with the ions and vanishes across the horizon, without radiating strongly, an outcome that naturally produces a dim appearance for a given mass supply. Some of the trapped energy can drive an outflow that removes mass from the inflow, further lowering the rate that reaches the center. Convection can also carry heat outward, and flatten density gradients again, reducing the central brightness. Each of these processes leaves broad qualitative marks rather than sharp spectral lines, and at the distance of this system, the limits on nuclear light constrain their net effect rather than their detailed partition. Timescales help to frame expectations. The inflow time from the capture scale to the innermost stable orbits in a hot flow is long compared with the orbital time, so the system can rearrange magnetically and dynamically many times as it drifts inward. The cooling time of the surrounding hot atmosphere at kiloparsec radii is even longer than a Hubble time, so the supply is not replenished rapidly by runaway condensation. The collision times for particles are short enough to define a common pressure, but long enough to allow separate electron and ion temperatures. Against this background of slow processes, only a major gas-rich merger could deliver a large cold reservoir and force a bright state, and the absence of cold gas and dust signs argues that no such event has happened in the recent past. Within measurement limits, then, the accretion environment in Abell 1201 is best understood as a low-supply, low-efficiency engine, operating far below its theoretical maximum, with most of the gravitational energy either carried across the horizon with the flow or tapped to launch weak compact outflows that leave only faint radio signatures. The engine's presence is known primarily through its gravitational pull on nearby stars and its imprint on the lensing geometry, rather than through its light. This picture fits the old quiescent stellar population, the hot, slowly evolving intra-cluster atmosphere, and the lack of strong nuclear lines or bright hard X-rays. It allows for small intermittent activity that keeps the core gently stirred without violating the strict limits on radiation, and it positions the central mass as a dominant dynamical actor that shapes orbits and lensing while remaining nearly invisible as a source of light. The relativistic domain around the central object in Abell 1201 is defined by scales that arise from general relativity rather than from the distribution of stars or dark matter, and for a mass on the order of 30 to 33 billion suns, these scales become vast in absolute terms, while remaining minute in angular size at the cluster's distance. The event horizon, which is the boundary from which light cannot escape, has a characteristic radius known as the Schwarzschild radius, that for a non-spinning case equals roughly 3 kilometers for each solar mass. Multiplying by tens of billions of solar masses gives a horizon radius of about 90 billion kilometers, which corresponds to a light crossing time of a little more than 3 days. The photon sphere, the spherical surface where light can in principle orbit in unstable circular paths, lies at 1 1/2 times the horizon radius in the non-spinning case, and the innermost stable circular orbit for matter in a thin disk lies at 3 times the horizon radius. If the central object spins as astrophysical black holes are expected to do, these radii shift inward for orbits aligned with the spin, and outward for orbits counter to it, but the precise spin is not measured here, so the discussion keeps to the non-committal range bracketed by these general results. The orbital timescales in this relativistic region scale in direct proportion to mass. For a non-spinning geometry, the orbital period at the innermost stable circular orbit is about 160 days for a mass near 30 billion suns, while faster spin could shorten this to a few tens of days for orbits that co-rotate with the whole. These periods are far longer than the minutes to hours seen around far smaller black holes precisely because time and length scales stretch with mass. Gravitational redshift and time dilation also grow strong near these radii. A clock that rides close to the photon sphere ticks markedly slower relative to a clock at large distance and light that climbs from deep in. The potential well loses energy and arrives redder. For a non-spinning case, the redshift factor at the photon sphere equals the square root of 2. Meaning the emitted frequency is reduced by this factor when received far away. Even larger shifts would appear for photons that begin closer to the horizon, along paths that still escape. The black hole shadow, which is the dark silhouette cast against any bright backdrop by the capture of light rays that cross the photon region, has a radius of about 2 6/10 times the horizon radius in a non-spinning geometry. That translates to a shadow diameter of roughly 5 times the horizon radius, or nearly 1/2 of a light month across for a mass of several tens of billions of suns. At a distance of about 2.7 billion light-years, this spans only a few microarc seconds on the sky, far smaller than the resolution achieved by current horizon-scale interferometers at this distance, which explains why the central object in this system is inferred through lensing geometry and dynamics rather than directly imaged at horizon scales. Tidal forces near the horizon depend inversely on mass, so for an ultramassive object they are comparatively gentle at the boundary itself. A star-sized body that could somehow approach on a safe path would feel smaller differential gravity across its diameter at the horizon of a tens of billions solar mass hole than at the horizon of a million solar mass hole. Only much deeper inside would the gradients grow severe enough to tear normal matter, and inside the horizon no signal returns. This scaling of tide with mass is one reason why ultramassive black holes can possess very large, calmly stratified spheres of influence in which stars move under a steep but smooth potential without experiencing catastrophic stretching until far beyond any observable boundary. Light propagation in this curved spacetime produces several characteristic effects that influence the appearance of nearby matter. A faint, thin disk that reaches inward toward the innermost stable orbit would appear brighter on its approaching side because of relativistic beaming, and would be lensed into a broadened ring-like outline by the curved paths of photons near the photon sphere. Multiple higher-order images of the same emitting patch would stack very close to the edge of the shadow, each one produced by photons that loop an additional partial orbit before escaping, though these images are exponentially fainter and would be undetectable at the cluster's distance. If jets were launched from the innermost region's frame dragging in a spinning geometry, would align their bases with the spin axis, and could impart a slow precession if the spin axis and any outer disk axis were initially misaligned, but again the scales here are so small in angular terms that only the integrated time-averaged radio core would be accessible, and it is faint. The energy conditions near the horizon set absolute caps and benchmarks. The Eddington limit, which compares outward radiation pressure to inward gravity, in a spherical flow scales with mass, so a tens of billions solar mass object has a very large formal limit, yet the observed luminosity sits many orders of magnitude below that level, meaning that the actual accretion flow, if present, must be both meagre in supply and inefficient in turning gravitational energy into light. In a general relativistic description, the specific energy of matter at the innermost stable circular orbit sets the maximum fraction of rest mass that an ideal thin disk could radiate before matter plunges inward. For a non-spinning hole, this efficiency is about 6%, and for a near maximally spinning hole in the co-rotating sense it can approach 40%. The weak observed light therefore implies that either very little mass reaches these orbits, or that the flow is too hot and too optically thin to radiate efficiently, which matches the multi-wavelength limits discussed at larger radii. Relativistic lensing also affects how the central mass influences background light at tiny impact parameters, but on galaxy scales the dominant lensing signatures come from the combined stellar and dark halo distribution, rather than from the horizon scale structure. The horizon scale features sit far below the resolution of the strong lensing maps used to weigh the compact mass. Even so, the same theory of light bending governs both regimes, with the central spike in potential acting as an almost point-like deflector at the tiny angles relevant to the inner counter image, while the extended components shape the broad arc. The space-time curvature can be summarized by the gravitational radius, a length scale equal to 1/2 of the Schwarzschild radius. For tens of billions of solar masses, this length is on the order of several tens of billions of kilometers, and many of the characteristic radii can be written as simple multiples of this scale, which aids in comparing different mass assumptions without changing the underlying physics. Infall times from the innermost stable orbit to the horizon are short of order, a few light crossing times of the horizon radius, so once matter reaches these radii it plunges rapidly. Any electromagnetic echo of that plunge would be brief on the intrinsic timescale, but stretched by mass it would still correspond to hours to days rather than to seconds. All of these properties together describe a central region, where Newtonian gravity gives way to the full structure of curved space-time, where orbits terminate at a last stable ring whose period is measured in months, where the photon sphere carves a shadow a few microarcseconds wide at the cluster's distance, and where tides at the horizon are gentle by virtue of the great mass, even as no light escapes once the boundary is crossed. These are local geometry-driven facts that follow from general relativity and from the mass range inferred at larger radii, and they define the physical scales within which any matter must move, shine, or vanish as it approaches the central object. The path by which the central galaxy of Abell 1201 and its compact object reach their present masses is written in broad strokes by the evidence already measured, while several details remain uncertain and are stated plainly. On the galaxy scale, the extended stellar envelope, the high specific frequency of globular clusters expected for brightest cluster galaxies, the shallow central light profile consistent with past scouring, and the close alignment between galaxy intracluster light and cluster halo, all point to a long history of assembly in which early rapid growth is followed by many later, largely gas-poor additions. Gas-poor or dry mergers add stars without much new gas, so they raise mass and size while keeping star formation low and preserving old stellar ages. The gradual color change from redder centers to slightly bluer outskirts, together with metallicity patterns inferred from spectra, matches a picture in which the inner body forms early in deep potentials, while the outer halo grows from stars contributed by smaller systems that fall in along filaments and are stripped. Kinematics show a pressure-supported system with weak rotation, also typical of an assembly dominated by many mergers rather than by the smooth growth of a long-lived disk. The diffuse intracluster light and faint tidal structures near the detection limit chart. The continued delivery of stars at large radius, where dynamical times are long and phase mixing is incomplete. On the cluster scale, the traxial dark matter halo the anisotropic infall region, and the smooth hot intracluster medium with only gentle disturbances indicate a mature node that still accretes along preferred directions, but has not experienced a violent recent major merger that would upset global profiles. Within this setting, the strong lensing arc and the faint inner counterimage require a steep central potential on galaxy scales and models that respect measured stellar gradients and realistic halo slopes, demand a very concentrated, nearly point-like mass at the center, whose value lies on the order of several tens of billions of solar masses. This mass need is robust across modeling choices that allow triaxiality, external shear, and small perturbers, while the exact figure carries marked explicit model dependencies. Stellar kinematics across the inner kiloparsecs agree with this structure by favoring a high central dispersion and a smooth decline that can be produced by a luminous stellar mass with a falling mass to light ratio plus an added compact term. Removing the compact term forces extreme assumptions elsewhere and degrades the fit. Multi-wavelength limits on nuclear light point to a present state of very low supply and very low radiative efficiency. These pieces together fix a consistent present-day structure, a massive old pressure-supported central galaxy embedded in a deep cluster, potential hosting an ultra-massive compact object whose sphere of influence stretches across thousands of light-years and accreting, if at all, in a quiet mode. Within that structure, several formation channels are physically plausible, and some are better supported than others by what is seen, but none can be singled out uniquely at this distance. Early rapid assembly at high redshift through frequent mergers among massive gas-rich progenitors can build dense stellar cores quickly and seed central objects that later grow by additional mergers. Later gas-poor mergers in a crowded cluster core enlarge the stellar envelope, and when the galaxies bring their own central objects, create black hole pairs whose gradual hardening eject stars on radial orbits and leaves shallow light cores. Tidal stripping of satellites deposits metal-poor stars and blue globular clusters into the outer halo and intracluster space, raising the specific frequency of clusters and broadening the spatial distribution. Each of these processes is observed in some form across brightest cluster galaxies, and the ensemble of signatures in Abell 1-2, 0-1 matches the general pattern. The growth of the compact object can proceed through two main channels: mergers with other massive black holes brought in by galaxy mergers and gas accretion. The quiet present rules out strong recent gas accretion, and the weak dust and molecular gas limits argue against large late gas-driven growth. The crowded merger history expected in the center of a rich node allows many black hole mergers over long times. The shallow central stellar light profile and the large sphere of influence are both consistent with the cumulative effect of past black hole pairs that ejected stars and deepened the central potential. How much growth comes from gas at earlier times remains open because the present state does not directly record distant epochs when gas fractions were higher. Scaling relations between black hole mass and galaxy properties provide context. Extrapolations of relations that compare mass to stellar velocity dispersion or to bulge stellar mass suggest that the most massive central galaxies can host very large compact objects, yet precise placement at the extreme high end remains debated because samples are small and selection effects are strong. The mass range inferred here falls among the largest reported and sits near or above simple extrapolations, which could mean that central objects in brightest cluster galaxies grow somewhat more than average through repeated mergers, or that stellar population assumptions in the inner body still allow modest shifts in luminous mass. Lensing-based estimates help by anchoring the total inner mass independent of stellar templates, while dynamics help by anchoring the shape of the potential. Together they reduce freedom but do not erase it, and the quoted uncertainties reflect this. Several specific uncertainties deserve clear restatement. The inner slope and three-dimensional shape of the dark halo introduce degeneracies with the stellar mass-to-light gradient and the compact term. These are constrained but not fixed. The external shear from nearby mass and the presence of small perturbers alter arc shapes and fluxes. Models marginalize over their plausible ranges. The centroid of mass relative to light and the point spread function in the imaging affect the exact mapping of the faint counterimage. Errors here are propagated. Line-of-sight structures contribute weak extra convergence and shear. These are estimated statistically and included. Within these bounds, the requirement for a concentrated central mass remains secure. The accretion mode is also constrained but not fully measured. Low infrared and X-ray luminosities and faint radio emission set strict limits on current activity, yet cannot prove the absence of intermittent small events that inject mechanical energy without strong light. The hot atmosphere shows no bright large cavities, so any recent jet power must be modest. Small mixed relics could fall below present depth. Cold gas limits are strong for large reservoirs, but allow tiny transient clouds. These caveats state the allowed ranges without changing the central picture of a nucleus in a quiet, low-efficiency state. Taken together, the data support a growth path in which early assembly builds the dense core and the first massive central object later dry mergers enlarge the galaxy and deliver additional black holes that merge at the center scouring a shallow stellar core, and the long-term environment of hot low-density gas suppresses sustained luminous accretion so that present activity remains faint. What remains to be learned follows directly from these uncertainties. A sharper map of stellar kinematics at smaller angular scales would better resolve the central rise of dispersion and narrow the allowed mix of stellar mass and compact mass. Deeper, higher resolution imaging of the arc and counter-image would tighten constraints on the inner lens geometry, the exact location of the radial and tangential critical curves, and the contribution of small perturbers. Improved multi-wavelength limits, particularly in hard X-rays, and in the millimeter band for cold gas, would further bound any hidden accretion. Wide-field weak lensing and denser spectroscopy of member galaxies would refine the global halo shape and external shear that enter the strong lens model. Each of these steps addresses a known parameter rather than opening a speculative path. In the meantime, the present description remains internally consistent: a central galaxy, whose stars and globular clusters record early deep collapse and long dry assembly. A cluster halo and intra-cluster medium that mark a mature node still fed along filaments. A strong lens whose arc and inner counter-image together demand a very concentrated mass at the center. Stellar dynamics that favor the same structure, and a nucleus that sits in a low state of supply and efficiency. This is the measured model-aware account of how the system stands today, and of the broad, well-supported ways it likely came to be, with clear statements of what is fixed by data and what is still bounded rather than pinpointed.